Okay, Algebra 2, this is it, our last lesson on rational functions. I promise you this will be a little shorter than the ones you've had to endure for the last couple weeks. Last thing we have to do is talk about how to solve a rational equation. So first we have to explain what a rational equation is, and then we'll get into the details of how you solve it, and then we need to revisit a problem that you've seen before this year, and that is extraneous solutions. So here we go. First, let's explain what a rational equation is. You guys should already know what a rational expression is. We've talked about that when we explained what a rational number is. Rational number is basically any number that can be expressed as a fraction. So that's what a rational expression is. It's essentially a fraction. Now, a rational equation would be any equation involving at least one rational expression. However, we have to be a little more precise about this. Take, for example, this equation. Some people might look at this and say, well, that's got a fraction, so that must be a rational equation. No, not really, because that fraction doesn't have anything to do with the variable. So this is really not considered a rational expression, or excuse me, a rational equation. That's just a linear equation. If you want to have a true rational equation, the variable has to be part of the fraction, has to be part of the rational expression. Okay, so once again, people might look at this and say, okay, that must be a rational equation because now the variable is in the fraction. But not really, because that's x divided by 2 is really just 1/2 times x. So that's really just a coefficient. So this also would not technically be considered a rational equation. And that's because, yes, the variable is in the fraction, but the variable is not in the denominator. So if you really want a rational equation, the variable has to be in the fraction, but more specifically, the variable has to be in the denominator of the fraction. Okay, so here finally is something that we would consider a true rational equation. It's a very simple one, but let's start off with a simple one and talk about how we solve it. Now, by now, I hope you realize that there's generally two different approaches to solving any equation. All year long, we have talked about solving by graphing or solving using algebra. So let's take a minute and talk about solving by graphing. I hope you recall that if you wanted to solve any equation by graphing, basically what you do is you graph the left side and you graph the right side, and then you look for where those graphs cross. Okay, so the blue graph represents the left side of this equation, and the red graph represents the right side. And you can see that clearly these graphs cross, and where they cross, that would be the answer. This calls to mind one of the limitations of solving by graphing. Whenever the point of intersection is not at a nice round number, it's going to be difficult to determine exactly what the answer is. So that's a problem we've discussed before. Something else we've discussed before, though, graphing is often a good way, though, of at least seeing whether or not you have a solution and how many solutions you have. So let's talk about that for a second. You can see from this picture that this simple rational equation has one solution. What if we considered some other possible pictures? So rational equations clearly could have one solution, but if I changed the other side of the equation, I hope you see that it would be possible to have a rational equation that had two solutions. Or if I change it again, I could have a rational equation that has no solutions. And why does the other side of the equation have to be a line? We never said it had to be. What if I did this? So now you can see that a rational equation might have more than two solutions. So again, graphing is just a nice effective way to see how many solutions you have and what the possibilities are. So be advised, when you solve rational equations, you might have no solution, one solution, two solution, maybe even more than two solutions. But let's go back and look at solving this problem by graphing, though. Now, again, this is not too hard to graph. In fact, if you needed to, I would hope that you could graph this by hand. This is another shortcoming of solving by graphing, though. If you don't have a graphing calculator, you'll have a hard time determining the exact point of intersection, and you'll have to draw the graph. Now, drawing this graph is not so bad, but what if you tried to solve this rational equation by graphing? That would be really hard. In fact, I'm going to confess to you that I don't really have a good idea of how to go about drawing that graph. That would take quite a bit of work. Or here's another good example of why solving by graphing could be problematic. Take a look at this equation. Now, once again, that is not the easiest thing to graph, but actually, if you took some time, I would hope you could figure it out. Now, if you have a graphing calculator, definitely it makes your life easier because I can let the graphing calculator draw the graph, and then that saves me a lot of work. It also makes it easier for me to find the point of intersection. But look at this last equation again, if I clear the screen. This last equation here, if I were to use a graphing calculator to draw that graph, it would look like this. And so here's one final cautionary statement about solving by graphing. When you look at that graph, how many solutions do you think that equation has? If you're saying it has 2 solutions, you're wrong. That equation actually only has 1 solution. We'll come back and talk about that last equation towards the end of the presentation. So basically, the bottom line is solving by graphing certainly can be done. It's easier to do if you have a graphing calculator. But even with a graphing calculator, you need to be careful solving by graphing. And it's because graphs of rational functions are so complicated. That's something I hope you already appreciate, given the last 2 weeks we've spent talking about graphing rational functions. So the rest of this time, we're going to talk about solving algebraically. Okay, well, let's just dive right into it. Solving rational equations algebraically can be broken into a few different categories. To be a rational equation, you have to have at least one rational expression. So let's start with that simplest category. What if you had an equation that only had one rational expression? Well, one way to solve that would be to multiply both sides by the denominator. In other words, on this example, I'm going to multiply the left side and the right side by x. Now on the left side, I just get 1, and on the right side, I have 2x. So now I need to divide by 2, and I get an answer. And if you went back and looked at the graph, I hope you would recognize that 1/2 is about where those two graphs crossed. So hopefully that answer makes sense. Let's look at another example, one that's a little more complicated. So again, I'm going to multiply both sides by the denominator, which means I'm going to multiply the left by x minus 2, and I'm going to have to multiply the right by x minus 2. Now, on the left side, it's easy because the x minus 2's cancel. On the right side, you're going to have to FOIL that. So here is the first, here is the outside, here is the inside, and here is the last. When you FOIL, you should always combine like terms. So now I have this. And I hope you realize you have a quadratic. So hopefully you remember how to solve quadratics. One thing you should definitely do is make it equal to 0. Because whether you're factoring or using the quadratic formula, you're going to want your quadratic to be equal to 0. Now, that quadratic, if you take a look at it, it does not factor. So if it doesn't factor, that means you may have to resort to the quadratic formula. Okay, well, the opposite of b would be 3, plus or minus the square root. B squared, -3 times -3 would be 9, minus 4 times a times c, all over 2a. And that should be the answer according to the quadratic formula. And if you simplify it, you get 3 plus or minus square root of 5 over 2. And that is simplified. And I hope you realize that that is 2 solutions. So you have 3 plus the square root of 5 divided by 2, and you have 3 minus the square root of 5 divided by 2. So if we were to go back and look at the original equation and consider it by graphing, if you were to graph these two functions, you would see that they cross in two different places. Let's look at one more example. Again, we're going to multiply by the denominator, so that's multiplying both sides by x plus 3. And again, on the left-hand side, the denominators just cancel, so that's pretty easy. On the right-hand side, I'm going to have to FOIL, so that's x squared. This time I'm going to go ahead and combine my like terms right now, if you don't mind. So that would be plus 7x plus 12. Once again, you have a quadratic, and you should make it equal 0. So if I move the x to the other side, that 7x will turn into a 6x. And if I move the 1 to the other side, that 12 will turn into a 13. Once again, this quadratic does not factor. If I try to do the quadratic formula, I get x is the opposite of b plus or minus. B squared would be 6 times 6, which is 36, minus 4 times a times c all over 2a. Now, 4 times 1 times 13, that's 52. So 36 minus 52, I hope you recognize what's happening here. 36 minus 52 is negative 16. I think I did that right. And the square root of negative 16 is imaginary. So what that tells us is there is no real solution. In other words, if you were to graph the original equation, what you would see is those two graphs never cross. Okay, let's move on to the next type of rational equation. What if you had two rational expressions on opposite sides of the equal sign? Well, this can best be handled by cross multiplying, which some of you might remember. In fact, some people call this butterflying. You might have had a middle school teacher or somebody else teach you that term. So if you cross multiply, the left-hand side would be x times x minus 1, and the right-hand side would be 2 times x plus 2. Okay, well, when I distribute, that's x squared minus x, and if I distribute on the left side, that's 2x plus 4. You can see, once again, you have an x squared, so this is going to be quadratic. So as we've been doing, any quadratic you should solve by making it equal to 0. So if I move the 2x to the other side, this will combine and become negative 3x. And I move the 4 to the other side, it's going to be a negative 4. And this time I believe I have a quadratic that can factor, because I think that would be x minus 4 times x plus 1. So when I factor the quadratic, I get the answers x equals 4 and x equals negative 1. And so you have two solutions. And once again, if you were to go back and graph the original equation, you hopefully would see that those two rational functions cross in two locations. Let's do one more example with cross multiplying. So if I multiply these and I multiply these, my left side would be 4 times x plus 1, and my right side would be x times x squared minus 2x minus 3. Now, maybe you can already tell what's going to happen here, but we're going to run into some trouble. When I distribute, my left side turns into that. My right side, notice I'm getting a cubic. Now that's definitely a reason for concern. So like a quadratic, you typically are going to want to make this equal to 0. So if I move everything to the right-hand side, the negative 3x and subtracting 4x will combine to get you negative 7x. And then when I move the 4, I will get over here, I'll get a minus 4 on the right. Now the problem is, how do I solve this cubic? Well, there's no cubic formula. The only way we know how to solve a cubic like this is factoring. The only kind of factoring that we could do is we could possibly factor out a common factor, but there doesn't appear to be one. And the only other type of factoring we would know how to do is factor by grouping. And if you look at this group and if you look at this group, well, there's no common factor in the second group, and so this doesn't factor by grouping either. So you get to a point where you're kind of stuck. Well, that's just going to happen sometime with rational equations because of what you're multiplying. I hope you realize that, if one of your if part of your rational expression is quadratic and part of it is linear, when you cross multiply, multiplying a linear and a quadratic is going to get you a cubic. And that just is a problem that can come up from time to time. So we're just going to table this for a minute and we'll come back to it later. So let's look at one last type of rational equation that you might have to solve. What if you had more than one rational expression, but they were on the same side of the equal sign? How would you handle this? Well, the easiest way to do that would be to multiply both sides of the equation by the least common multiple of the denominators. When I say least common multiple, what we need you to do is look at all the denominators. You have x plus 2, x minus 1, and then you have another x plus 2. So that means the common multiple is going to be x plus 2 times x minus 1. So that's what we're going to multiply the left hand and the right hand side. Now, let's do the right hand side first because that would be the easiest. On the right hand side, the x plus 2 and the x plus 2 cancel. So on the right hand side, all you get is 2 times x minus 1. Now on the left hand side, it's going to be a little more complicated because you have to realize that all of this is being distributed. You're multiplying it by that and you're multiplying it by that. Now on the first term, the x plus 2 is going to cancel with the x plus 2. So on the first term, what you're going to end up with is x minus 1 times 1. And there's no denominator because the x plus 2 canceled. How about the second term? Well, on the second term, the x minus 1 is going to cancel with the x minus 1. But you still have this though, because this is not canceled anymore. It only canceled when you multiplied by the first fraction. So that means the second term is now going to be x plus 2 times x. Now, I hope you're able to follow what I'm saying there. I know that might have been a little confusing, especially the way I wrote it on this slide. So let's clean up what we have here. So this term is just x minus 1. Here, I have to do some more distributing because that x is being multiplied by the x plus 2. So you're subtracting, sorry, let me change my color back. You're subtracting x squared and you're subtracting 2x. And all of that equals, on the other side, you also have to distribute. So on the other side, you have 2x minus 2. Now, I hope you can tell you've got a quadratic. So as usual, you're going to want to make one side equal to 0. I'm going to make the left side equal to 0. because I'm going to move my my x squared over to the right so that it won't be negative. So there's my x squared. I've got to gather up all my x's. I have 2x. When I move this, I'm going to add 2 more, so that's 4x. But then I'm going to move this by subtracting. So 4x minus x leaves me with 3x. And when I keep combining like terms, this is a minus 2, and I'm going to move that by adding 1. So if I add 1 to the minus 2, that leaves me with a minus 1. So there's my quadratic, x squared plus 3x minus 1. That quadratic does not factor. So once again, I will have to resort to the quadratic formula. X is the opposite of b, plus or minus the square root. B squared is 3 times 3, so that's 9, minus 4 times a times c. My c is negative 1, all over 2a. So if you clean that up, you have negative 3 plus or minus. This would be the square root. You're actually adding the 4, not subtracting, because of this negative 1. So that turns out to be the square root of 13 over 2. And so once again, you can see you have 2 answers. Negative 3 plus the square root of 13 divided by 2, and negative 3 minus the square root of 13 divided by 2. So let's go back and look at this equation that we tried to solve earlier by cross multiplying. We saw that when we cross multiplied, we ended up with a cubic, and we moved all the terms to one side, and we tried to solve that cubic by factoring, but we couldn't do it because there was no common factor and we couldn't factor by grouping. Well, another way to solve that cubic would have been to graph it and find the zeros. Now, you might be thinking, well, if I'm going to solve by graphing, why don't I just graph the original equation? And that's a fair question to ask, except I would just point out that it's probably easier to graph this cubic than it is to graph those rational functions. So I still think cross multiplying and then graphing is probably a better way to go. Anyway, if you graph that cubic, here's the graph, and I used a graphing calculator obviously to generate this graph. You can see that it has 2 zeros, negative 1 and 4. So those are the solutions to the cubic, and you would think that those must be the solutions to the equation. Well, it turns out that yes, 4 is a solution, but negative 1 is not a solution. Why is negative 1 not a solution? Well, because go back to the original equation and notice what happens if x is negative 1. If x is negative 1, you would be dividing by 0, which is always a no-no. See, with rational functions, you have to remember you're never allowed to divide by 0. Any number that makes you divide by 0 is considered a domain restriction. Those values have to be excluded. And I'm talking about the original equation, not any equation that you get after you've manipulated it by cross-multiplying or doing something like that. Now keep in mind, dividing by 0, that is what causes rational functions to have things like vertical asymptotes and point discontinuities. See, let's go back and look at this equation that we showed you back when we were talking about solving by graphing. This was an equation that we showed you, and we showed you the graph. And when you look at the graph, it looks like there are 2 points of intersection, so it looks like there should be 2 solutions. But we told you in the beginning of the slideshow that this equation actually only has 1 solution. Well, let's take a closer look at this graph. It looks like the graphs are crossing when x is 3 and when x is 5. Well, let's take a closer look at what happens at those two numbers. What happens when you plug in 5? Well, if you plug in 5, 5 minus 4 is 1. And then on the other side, you get 5 minus 3, 5 squared minus 7 times 5 plus 12. Okay, 5 minus 3 is 2. 5 squared is 25. 7 minus 5 is 35. 25 minus 35 is negative 10. Plus 2 is, plus 12 is 2. So that works. 2 over 2 equals 1, and that works. So 5 is a solution. But what happens when you plug in the 3? Well, if I plug in 3, 3 minus 4 is negative 1. And on the other side, 3 minus 3, maybe you can already see what's happening. 3 minus 3 is 0, and 3 squared is 9, minus 21, plus 12. That's 0 over 0. And 0 over 0 does not equal negative 1. So why doesn't the 5 work? Well, because if you didn't realize it, if you think about what you hopefully know about graphing rational functions, look at that denominator, x squared minus 7x plus 12. That can be factored, and it factors into x minus 3 and x minus 4. And you see what's happening right here? You have a hole at 3. You have a hole at 3, and your graph looks like that. So your graph looks like 1 over x minus 4, but you have a hole at 3. And so when you're looking at this graph, you think you're seeing a point of intersection, but right here is a hole. So where you think you see the graphs crossing, they're actually not crossing because the red graph doesn't exist at 3. Okay, well, that was a little bit shorter than the last few slideshows. I know it was still a little on the long side, but I hope it wasn't too bad. I hope you now have an understanding of what makes a rational equation, and I hope you have an idea of how to solve it. You can solve by graphing, but just be careful. Even if you had a graphing calculator, sometimes you can get tricked because holes don't show up clearly when you look on graphing calculators. If you're going to solve algebraically, there's some different strategies you need to employ, whether it's multiplying by the denominator, cross-multiplying, or multiplying by the least common multiple. And then the last thing is just be careful. Whenever you think you have an answer, make sure you go back to the original equation and make sure none of your answers are making you divide by 0. Because if they are, they're not valid answers. They're extraneous. So with that in mind, if you would go to It's Learning, look in the Unit 10 folder, you should see in there an assignment called Solving Rational Equations. Because we're getting towards the end of the school year, this assignment is not going to be one where you can submit your answers an unlimited number of times. We're just going to give you 3 chances at answering these questions, and your score will be whatever your best score is after 3 attempts. So you can solve the equations however you prefer, whether by graphing or algebraically. Just be careful and make sure you double check your answers. Make sure that you're not entering any extraneous answers. And if you do have questions or need help, of course, you can reach out to me by email or through the discussion boards. So good luck, And that's going to take care of our unit on rational equations.